Hello, this is SND College of Engineering and Research Center, Yeola, lecture series for first year engineering. I, Dr. Chaudhary Vivek Sitaram from first year engineering department. Now, in previous lecture, we had seen about the resistivity, conductivity and distribution or classification of the material depending or with respect to conductive, that is insulator, conductor and semiconductor. Now, in that we had seen about the semiconductor, that is from fourth group and third group and fifth group, fourth group material, third group, fifth group material and second group, sixth group material. The interesting properties of semiconductors emerges when impurities are doped, and that is nothing but the doping. Doping is the process of adding very small well controlled amounts of impurities into a semiconductor. Doping enables the control of the resistivity and other properties over a wide range of values. For silicon, impurities are from column 3rd and 5th group of the periodic table. So third group, boron, aluminum, gallium, indium, and fifth group, pass up, antimony, bismuth. So when we are doping fifth group element, what happens? In the outermost orbit there are 5 electrons, and in silicon having outermost orbit 4 electrons. So 1 electron is more over here. So when phosphorus added, the other column 5th element, the atom replaces silicon atom in a crystal lattice. Since phosphorus has 5 outer shell electrons, there is now an extra electron. Material is still charge neutral, but very little energy is required to free that electron for conduction band. If we are visualizing this diagram, so as due to 1 electron, silicon doped by pentavalent impurity, that is from phosphorus, just like each dopant atom donates 1 free electron. In this is thus called donor, and the doped semiconductor becomes N-type material. So now, if impurities from the third group is added, that is trivalent, then we are just like a boron, aluminum, gallium, indium, then there is a deficiency of 1 electron. That's why 1 hole is present over here. So as 1 hole is there, then 1 electron is more, but 1 hole represent. So because from the third group element, outermost orbit are contain only 3 electrons. So 1 electron is vacancy over there. So semiconductor becomes p-type semiconductor. So acceptor impurities are the hole which are accepting. Hole is propagating through a silicon. And when hole propagate through the silicon and doped silicon carrier concentration, now one can calculate how to calculate doped silicon carrier concentration. If N is greater than P, the material is N-type. If number of electron concentration is more than number of hole concentration, the material is N-type. If the hole concentration is more, that is if the acceptor impurity is more than the donor impurity, the material is P-type material. The carrier with the largest concentration of majority carrier, the smaller is the minority carrier. So donor impurity and acceptor impurity. So charge neutrality requires according to that. Now in N-type material, so number of donor impurity is more than the acceptor impurity. So we are considering here according to that. And in N-type material over here. And in P-type material, acceptor impurity is more than the donor impurity. So we find the majority carrier concentration from charge neutrality and find the minority carrier concentration. And then now practical doping levels. Majority carrier concentrations are established at manufacturing time and are independent of temperature. However, minority carrier concentrations are proportional to Ni square, a highly temperature dependent term. Now, as we know, N is approximately equal to donor impurity minus acceptor impurity for N-type material and acceptor impurity minus donor impurity for P-type material. And if we observe the mobility and resistivity in a doped semiconductor material, so there you can observe that the total impurity concentration in n-type material and mobility here. Impurities degrade mobility atoms. Different size disrupt the lattice atom ionized, electrons scattered. Okay, so according to this side. Now diffusion current. In practical semiconductors, it is quite useful to create carrier concentration gradient by varying the doping concentration or dopant concentration and or dopant type across the region of semiconductor. This gives rise diffusion current resulting from the natural tendency of the carriers to move from the higher concentration region to low concentration region. Diffusion current is analogous to a gas moving across a room to eventually distribute itself across the volume. So in the figure we can or you can observe that whole concentration from higher density to lower density it is given here. Similarly, there is a electron concentration. So if the total current in semiconductor for n-type material and for p-type material. So from this semiconductor energy model we come over here. So semiconductor energy band model, the conduction band energy and valence band energy are the energy levels at the edges of the conduction band and valence band. So here electron participating in a covalent bond is a lower energy. So when temperature increases, that electrons from the valence band jumps into the conduction band, overcomes the band gap energy, and they will take part in the conduction. So energy bond model of a semiconductor material here for the holes. So integrated circuit fabrication overview. So whenever we want to see the integrated circuit fabrication, there is a base material is of n-type silicon material, then photoresist material is applied over there. So semiconductor silicon dioxide insulating material is given over here. There is a mask which is supposed to expose light, and the how much doping is there, according to that there is a formation of the windows, and from that p-type material can be doped over here. And as per our requirement we can dope different materials. Thank you.